As we go on to topic 8.3, I just want to remind you that if you were to go to your MyLabs Plus course content, Chapter 8, we're going to do 8.3, and there are 3 categories here. You could actually watch video presentations by authors of our text, as well as, of course, find the multimedia e-text, which is what we use for our discussion. We've done this throughout the course, and that's where it is. And it's loading, and we'll start our lesson shortly. In topic 8.3, we're dealing with an introduction to probability. So a little background. They're talking about going to a pizzeria and you order 2 large pizzas and they cost this much each. Then you are pretty certain this is what you'll pay at the register. You might pay tax as well. But for instance, does the owner of the pizzeria know how many clients will be in that day to order pizza? And the answer is no, because you have the public out there and they're going to decide they want to get a pizza that day. So the ones who come in, to a sense, it's random. So we think of a random phenomena, and the word phenomena, you may know, means just something that happens. So random happenings. And this then leads to this discussion of probability of an outcome. So some key words as we go, random experiment. So if you, for instance, have a coin, that one side we consider a head, and the other side we consider a tail, and we were to flip that coin, it's either going to be a head or a tail. But again, if you're flipping it in a random way, we don't know which side will come up ahead of time. So the flipping of a coin is a trial. What happens and what you get when you observe your results, that's the outcome. And then what kind of events can you have? Well, as we said, you can have a head or you can have a tail. This is considered your sample space, and we denote that with the letter S for sample space, and we define it in roster notation as either a head or a tail. So jumping into example 1, and given the sample space, and we have this little wheel with a indicator on it that we can spin around. Well, notice 1, 2, 3, 4, 5, 6, 7. It can land on 7 possible spaces. Now, it might land on the line a little bit, but that hopefully will not happen too often here. The outcomes are, as listed in roster notation, so our sample space is 7. Now, for the purpose of public opinion poll, responses are classified as young, middle, aged, and then senior, and as male or female. So you then designate young male, young female. And we have colors here. Middle-aged male, middle-aged female, senior male, there I am, senior female. So we're looking at our kind of survey and then developing a method to see what our sample space would be. And here, of course, there are 6. And here there were 7. And again, we're looking for our sample space. So for letter C, an experiment consists of studying the number of boys and girls in families with exactly 3 children. Let B represent a boy, which is obvious, and G represents a girl. So we have 2 that we're going to take 3 of. So we mentioned this formula before, and we'll be getting back to that later too. So our total possibility will be 2 to the 3rd power, which is 8. But let's look at it in some detail, and this is in your booklet as well. So we start off with a boy or a girl. That's what could happen first. And then from this one, we can have a boy or a girl. And from this one, a boy or a girl. And then so on and so forth. Now we're going to trace the lineage of following this line here. So right here, we have boy, 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 which is what they're listing there. And then we go there, there, but now swing over. This could be another possibility. Boy, boy, girl. And then going up here, boy, girl, boy. Boy, girl, boy. And that's how they do it to end up with all 8 possibilities. And that is our sample field, our sample space. Now, within the sample space, we have the events. And that's what they're describing here. An event is an outcome or a set of outcomes of our random experiment. So again, our sample space for tossing coins was head and tails, but the event, when you flipped it, was a head. That is the outcome of the experiment. Something that they will be using throughout this area is a die, which is one of a set of dice. The singular is die. And on it, again, there are 6 sides to it. And on each side, there's a number. Actually, it's a dot. And on one side, it'll be a 1 dot. And on another side, there's a 2. And then on this front side, there'd be a 3. Then a 4, a 5, and then a 6. So your sample space of a die is 1 through 6. Now, again, what event might you be looking for? So in this first event, you might be looking for an even outcome, 2, 4, 6. Or you might be looking for the die to show a 1. Or the die to show a number less than 5. And to show a number in which there are multiples of 3. So what they will do is set up the standard or the description of the event that they're looking for, and then this would be your sample field, in a sense, or your event that you're looking for out of your sample field of 6. So with that as background, let's look at these. And we are looking for, again, events. And what is our sample field? So in letter A of example 2, we're looking at example C, 1C of the previous page, and that's in your booklet. Event H, the family has exactly 2 girls. So take your finger and go through your previous list, and which contain 2 girls. Well, we have 3 events that contain 3 girls. All right, event K. The 3 children are the same sex. Well, you have one in which there are 3 boys, one in which you have 3 girls. So there's 2 events that would satisfy that. And then event J, the family has 3 girls. Well, there's only one of them that satisfies that condition. Now, again, as you read these, you need to be very careful about what they're asking. For instance, if an event E equals the sample space, then that is a certain event. And then if the event you're looking for is not within the sample space, then that event is an empty set. So we often say that when we're dealing with probability, it's going to be something greater or equal to 0 to our event that we're looking for, or less than or equal to 1. So when we deal with probability, it's usually some percent that's greater than 0, although if the event does not happen, cannot happen, then it would be 0. And if the event were a certainty, it would be 1. So it's some percentage between this. And they'll be giving you examples of this as we continue with our discussion here. Some very basic things in example 3. Suppose a fair die is rolled, and the sample space, of course, is this. Find the requested event. Well, the event that the die shows a 4 is going to be, in roster notation, just the 4. The event, the number showing, is less than 0. So there are no, or I should say less than 10. The event in our sample space, there are 6, so that there are 6 possibilities that it will show less than 10. I was thinking they're going to show 0 here. There's no 0 on the die. But in letter C now, the event that the die will show a 7. Well, here, there are no 7s, so this is going to be an empty set. There is no such event. It is an impossible event. Now, since events are sets, we can use set operations to find unions, intersections, and complements of events. So here is a summary of set operations for events. And recalling our Venn diagrams to help, here we're saying This is our sample space. This is set E, set F. When there's an AND, we're talking about intersection. There's the symbol. If it's an OR, we're talking about union. There's the symbol. And E complement occurs when it's everything but E, and E does not occur. Okay, so kind of keeping that in mind. So in example 4, we have a group of college students, and E is, the student is under 20 years old, so this would be under 20 years old. This would be our group of college students is the universe. So they're asking for what is E complement. E complement would be all those students that are 20 years old or older. This would be less than 20. This would be greater or equal to 20. In part B, we have F prime or F complement. F is a male student, so F complement is not a male student. So here we're asked F, not a male student, intersecting with G, which is a business major. So this would be a female business major. And as they're describing it, it's a not male student and is a business major. That is, the student is a female business major. So in letter C, we have E complement or E prime, and therefore E was under 20 years old, so E complement is 20 years old or over, and all of the business majors, because here we are putting them in union, and they stated here too. And this would be all students regardless of their major. It's not just that. These are all students that are over 20 or over. Grouping them with business students, but all students as well, because this is a very big group on this side. Again, for background, two events that cannot occur at the same time, such as getting both a head and a tail on the same toss, are called disjoint events. So disjoint events sometimes are referred to as mutually exclusive events. That is, both can occur at the same time. And the rule for it is that if the intersection of E and F is an empty set, this is a disjoint event. Now, in a sense, you can sort of see it here, that if the event G is a 1 and a 2, and event E is a 4, 5, and a 6, they can't occur at the same time. They are mutually exclusive events. They are disjoint events. I would have said disjointed, but they don't use the ED there. In example 5, we see this is the example. Are these disjointed events, or a disjoint event? And the answer is yes, because there is no intersection. So we're finally getting into a definition of what probability is. For sample spaces with equally likely outcomes, the probability of an event is defined as the probability of an event is equal to the event that you're looking for as a ratio or out of the total sample space. So, if you're looking for a 1, when you roll a die, there is on the die that one spot out of how many? 6 possible. So the event for rolling any one die, any number that would come up 1 through 6, is 1 out of 6. And if you add up all these possibilities, I have to put pluses between them all here, that will equal 6 out of 6, which is the whole. The whole is the 1. That is your 100% of what can happen. And that you'd get a 1 or a 2 or a 3 or 4, a 5 or a 6. Each is 1 out of 6, and that added together gives you your whole. That is the definition of probability of an event. Now for example 6, suppose your event that you're looking for in your sample space, again we're working with a die, there are 6 possibilities, and you're saying that it would be an even number. Well, there are 3 even numbers on a die, so your probability is 3 out of 6, which is 1/2. And letter B, the die will show a number less than 10. Well, again, your sample space is this, and all of these are less than 10, so there's 6 of them out of 6. That would be 1, the whole, and that the die would show an 8. This is an impossible event because there is no 8. So 0 divided by 6 is 0. Now, something else that's quite often used in probability is the standard deck of cards that contain 52 cards. There are 4 suits, a hearts, a club, diamonds, and spades. There are 13 cards in each suit, and there are the diamonds and the hearts that are red. The spades and the clubs are black. And each suit has an ace, a king, and a queen, and a jack. And then they are numbered 2 through 10. The jack, queen, and king are called face cards. And in a sense, if you wanted to give them a number value, would be 11, 12, and 13. Where the ace, even though we think of an ace as something special, has a value only of 1. So here we see a 52 card standard deck with the hearts, clubs, diamonds, and spades, and the face cards are the jack, queen, and king. So again, we're dealing with the sample space, and depending what we're looking for, you want to know where to get the numbers from. So I guess this is your license to look at a deck of cards. So let's get started with example 7. So we'll start off easy, and we are assuming the deck is well shuffled. That is, it's been stirred up and mixed and all those kinds of things they can do with cards to put them in a random order. That you're going to draw an ace. Well, an ace, how many aces in a deck? There are 4. So therefore, it's going to be 4 out of 52 that you then simplify to 1 out of 13. That you're going to draw a face card. Well, there are 12 face cards in a deck, so 12 out of 52, and here you can take a 4 out of each one, and it's 3 out of 13. That you're going to draw a spade. Well, there are 13 spades in a deck, so 13 out of 52 simplifies to 1 out of 4. In letter D, that you're going to draw a spade, and there are 13 of those, or, this is going to combine, a heart. So here this is union, so we add the 13 and 13, get 26 out of 52, which simplifies to 1/2. Now in this next part, they're suggesting something we've already done here, that for any event, if it's impossible, it would be 0. If it's a certainty, it's going to be 1. But generally, the probability of that event is between these. Now here we're going to look at some background, and I'm not going to read it to you, but just describe it, that in many real-life events, the sample space, it's not equally likely. So here they're talking about manufacturing sinks, and they wonder, sometimes a defect will occur. Well, what's the probability of the defect? Well, they look at one sink and there is no defect. So that's 0 probability. But they look at the second sink and there is a defect. So now you have 1 no defect, 1 defect, so the probability is 50%. And then you keep producing the sinks and you start to get data that give you what is called the relative frequency probability. That is, with your data, you are finding what is called empirical probability. That is, from actual real-life collection of data, what is the probability? Now, so far, we've been using mathematical probability. If it was an equal event and there were 6 sides, then it's equal. But here now the defect is really a random event. You don't want defects, but what actually is showing from the data you collect. Now, as you collect more and more data, your probability actually becomes a little more dependable, because you know that over the long run, and we speak of what is called the law of averages, that through large numbers, various trials, and in the study of genetics, we use this. This is part of my background in biology, that when we would do genetic counts, we would collect data and see how it would compare from our empirical collected data to our mathematical, hypothetical, theoretical possibility. So the use of these graphs now show the influence of having much data. So here we had when only one that had no defect, and then our second one that did, plotting this out of 100%, and then collecting more and more data, you see what happens. It tends to balance out at that you're going to get like in 1 in 4 will show a defect. Again, I would probably shut that down if I were the manufacturer. That's not acceptable, but again, I don't. This is just for illustrative purposes here. But you can see when you have little data, there's quite a difference, but then as you start to get lots of data, it tends to move, and now we have 1,000, to give us a pretty good idea of what the probability of having one with a defect would be, and of course the others are without defect. And they're also giving us this important note that independence here is assumed that what happens to one sink doesn't influence the outcome of what happens to the next sink that's manufactured. Now, example 8 is split over 2 pages here, so let's pick up what we're going to look at on the next page. Social science, that they ask this question, and let me highlight that as we go along. Do you feel your standard of living is much better, somewhat better, or about the same, somewhat worse, much worse than your parents? So you have 1, 2, 3, 4, 5 categories, and this is your frequency, and your sample space was 100 or 1,308. So when you are estimating the probability that a resident feels his or her standard of living is much better than that of his parents or their parents, you go to much better. This is the event you're looking for, 413, out of the total, and you get an approximate 30%. And that's how they do statistical analysis of what the population feels. So looking at B, we're going to estimate the probability that event B, that their standard is worse. Well, for that, notice we want to somewhat worse or worse, so we're going to have to group those 2 categories together, 162 and 69, which then gives us a total of 231, and we get about 18%. Now again, part of this is important of what is your sample space. were they Democrats? Were they Republicans? Were they independents? Were they anarchists? Were they disgruntled people? Always pessimists, optimists? Again, people who do this type of survey have to take lots of things into consideration, but hopefully it's a standard, fair, randomly selected group to get your data from. So we'll take a look now at a summary of properties of probability, where S is the sample space consisting of all the events that are possible, and the probability of an outcome, we say, is between 0 and 1, where each of the events that we're dealing with are between 0 and 1. So the sum of the probabilities, once again, as we mentioned before, is 1. And there are some exercises that we might look at if we have time. But